Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. Now, we've seen in this playlist how important the tool of Hilbert Series are in studying invariant rings. And what I want to do in this video is to show you Molien's beautiful formula for calculating the Hilbert Series of polynomial invariant rings. Okay, so let's see what our setup is in this video. In this video, we'll work over the complex numbers to make life easier for us. And in particular, we're in characteristics 0, so we can divide by any non-zero number that we like. Okay, we start with some finite group G. This is only a formula that concerns invariance with respect to a finite group. We'll also consider some linear representation of this G. So that's a map phi, a group homomorphism from G to GLV, where V is some vector space over C. And we'll suppose this vector space C has finite dimension R. And so perhaps it has a basis x1 up to xr like that. Okay, so once we have this set up here, we also know that G not only acts on this vector space here, it also acts on the polynomial ring C with variables x1 up to xr. Okay, we'll call that polynomial ring P. And what's nice about this ring, remember, is that this is also a graded algebra over C. Okay, so you can grade it in various ways. We'll just grade it the usual way, where each x1 up to xr have degree 1. So the pnth piece just consists of those terms or linear combinations of those terms which have degree n. Okay, so you've got this direct sum decomposition, and that makes this a graded vector space and in fact a graded algebra. Okay, so that's the setting that you need when you want to talk about Hilbert series. Okay, and the next point is to realize that this action is also graded. So when we look at the invariant ring, we can also talk about gradings and use that technique. Okay, so what does it mean to be graded? That means if we pick any group element G, okay, we let it act on this polynomial ring, it sends the nth graded piece, Pn, back to Pn. Okay, so that just means that if you apply this group element on a degree n element, you'll get a degree n element. Okay, so this is clear for degree 1. And since the group acts by algebra homomorphisms, that means that it sends degree n elements to degree n elements. Okay, so that's a statement of what happens here. Okay, so let's move on into the ring of invariants R. So that's PG, all those polynomials which are fixed by the action of all the elements of the group. And the key point is this is a graded subspace. Okay, so let's remind ourselves why that's true. Okay, so to be a graded subspace, that means that R equals the direct sum of Rn. And each of these Rn's should be subspaces of the corresponding Pn's. Okay, so why is that true? In fact, you can take the Rn to be what? You can just take it to be the nth graded piece Pn. So remember, it has to sit inside this Pn, and it also has to sit inside R. So you just make it Pn intersect R. Okay, that's what we'll make it equal to. Okay, so you can set these to Rn equal to this. And just to think a little bit more about what this actually equals, remember R is just the invariant inside P, the ambient polynomial ring. Okay, so what this equals to is just the invariance inside Pn. Okay, things which are invariant and also are in Pn are just the invariants of Pn. Okay, so it's quite easy to prove this result. Okay, certainly it's clear that each of these Rn's which are in here, because the Pn's are linearly independent, so are the Rn's inside here, and the Rn's certainly sit inside here because we got them by intersecting with R. So this is a direct sum and it sits inside here, okay, this right hand side, and the key point is that actually the sum of all these subspaces is in fact this one over here, and that's quite easy to prove too, and I'll leave that for you as an exercise. Okay, great. Once you have a graded subspace, you can talk about its Hilbert series. So just to remind you what that is, this is a power series. Okay, so we'll denote it with PGT. Okay, so it suppresses the notation of the representation phi, which really ought to be in there because that's part of the data. But we'll just write it as PGT. Okay, it's the Hilbert series of this graded vector space R. It's this power series where the coefficient of t to the n is just the dimension of Rn. Okay, so basically it records all these dimensions, but it puts it into this power series, and as we've seen before, this is a useful way of recording that information. Okay, so let's now see what Molien's beautiful formula is for this. Okay, and it's the following. Okay, it turns out to be an average over the group. Okay, so it's 1 on the order of the group times the sum of all the group elements of this expression here. Okay, let's just unravel this expression a little bit. So you look at the identity on V. This is a finite dimensional vector space. You have the identity on V. You look at phi of G, which is also an element of G of V. So this is an element of G of V. This is an element of G of V. And you multiply it by the scalar T. Okay, so this is for each T, right? Multiply by the scalar T. So that gives you some element of GL of V. So you can take the determinant of that, but it will depend on T. Okay? And so here you'll have a function of T. You take the average of those functions of T, and that's your answer for the Hilbert series. Okay, what's really nice about this is that you can see straight away, and one of the nice things about Hilbert series is, of course, the information here is infinite. There's an infinite number of these dimensions of Rn's. Okay? What you see here is a finite sum here as opposed to an infinite sum. So it turns out that one can see quite easily that this is actually a rational function of T. So we've compressed the information, all this information, into a rational function of T. So we just need to know the numerator and the denominator, and that's all the information you need. Okay, so to get a bit of a feel, let's look at a little example of this formula in action. Okay, and the example I want to have a look at is the ordinary double point. That's the easiest one, and it has a lot of interesting features already. Okay, so we've computed the Hilbert series of this already, but I want to show you how Molien's formula gets it to you very, very quickly. Okay, so we look at the ordinary double point, and it has a coordinate ring, and the coordinate ring is expressed as a polynomial invariant ring. Okay, so you look at the polynomials in two variables, x1, x2, and you look at the invariants with respect to a group, and the group is just a group of order 2. Okay, the cyclic group of order 2, 1, and sigma is the non-trivial element inside here. Okay, so to give the representation corresponding to this, I need a group homomorphism from G to GL of the vector space spanned by x1 and x2. Okay, what's that? So of course it's a cyclic group. To get a group homomorphism, I just need to send sigma to some degree 2 element inside here, order 2 element inside here. And the one that I'll send it to is the negative of the identity. So remember the ordinary double point, that's gotten by looking at a group quotient, okay, on the affine plane, where you send any point to its negative. Okay, you identify a point with its negative, and that gives you the ordinary double point. Okay, so the corresponding thing on the dual algebra side is you look at this polynomial ring of invariants. Okay, so let's so we have all the data that we need to construct this invariant ring, and also to apply Molien's formula. Okay, so we need to do an average over the group. There are 2 elements in the group. Okay, so there are 2 terms in the sum, and we take the average, so we have to multiply those terms by 1 on the order of the group, so half here and a half there. Okay, so let's see what this term here looks like. Okay, so you have the identity on V minus phi of GT, so you take the determinants of them. Okay, so to calculate the determinants, as usual, you pick a basis. So we can pick any basis we like, but x1 and x2 are the obvious choices. Okay, so the identity, what is that with respect to any basis, of course, is just this identity matrix here. Look at the identity matrix here as well. And then you have to look at phi of G for the 2 group elements. So phi of the identity element, phi of 1, is just, of course, the identity matrix here. Okay, and phi of sigma is the negative of the identity matrix, so that's this one here. Okay, so here we have in the denominator the determinant of the identity matrix, okay, minus a scalar matrix, which is the scalar t. Okay, and here we have the determinant of this scalar matrix with 1's on the diagonal minus the scalar matrix with minus t's on the diagonal. Okay, so now we just compute, and it's a simple exercise to do that, and let's see what answer we get. Okay, so first note that, of course, when you look at this setup, the types of things that you should get are indeed rational functions. Okay, and that's easy to see from the next step. Let's look at this term here, right? It's linear in all the entries. Okay, and in fact, here it's just going to be, since these are scalar matrices, a scalar matrix, and it's going to be this scalar 1 minus this scalar t, 1 minus t. That's a scalar matrix. Okay, so more generally this could be more complicated, but it's t times some constant matrix, like t times some constant matrix, so you'll get all linear terms in here, and when you take the determinant of that, that's a polynomial. Okay, on this side, the 5g now is this one here, so you have 1 plus the scalar matrix t, so you have 1 plus t as your scalar matrix here. And now it's easy enough to compute these determinants. Okay, here you have half in the numerator, and you just get the product of the diagonals, 1 minus t all squared. and here you get half in the numerator, and the product of the diagonals 1 plus t all squared here. Okay, and then if you put these on a common denominator, okay, so that's what Molien's formula gives you directly, and we know straight away it is indeed a rational function. But that's not the answer that we computed last time. When we computed it last time, we had these on a common denominator, which is 1 minus t all squared times 1 plus t all squared. And when you do that, of course, you add the half times this plus half times that. So in the squares, you get a minus 2t here, which cancels with a plus 2t here. And you just as the square of 1 and the square root of t, they contribute half each in here and here. So you get 1 plus the t squared. So this is the answer that you get. And you note that this is exactly the same as the answer that we saw in the video on Hilbert series. And in that case, we computed it quite differently. We actually computed what this ring was. Okay, and then we wrote a form for that. Okay, we wrote it in terms of a polynomial subalgebra and another direct summand. And we use various tricks about Hilbert series to compute what this is. But this is a lovely formula that allows you to get at the Hilbert series without even calculating what is the ring of invariants. Okay, so let's prove Molien's formula here. And the thing that we'll use is the Reynolds operator. And there's a Reynolds operator for each graded piece Pn. Okay, so for each natural number n, okay, remember there's a Reynolds operator, we'll denote it here rho n from Pn. It projects onto the fixed subspace Png, and of course we can include that into Pn. Okay, so that gives you a projection operator from Pn to Pn, whose image is the fixed subspace. And to remind you how that worked, where does it send some polynomial in this Pn? Okay, it basically sends it to the average over the orbits. So P natural, it sends it to P natural, and this is just 1 on the order of the group times the sum of all the g dot p. So it's the average over the orbit. Okay, so how do we use this? Okay, the way we use it is through the following lemma. Okay, so remember the Hilbert series of this invariant ring, so PG, is uses coefficients which are the dimensions of this PGN. Okay, so to get our hands on this, we're going to work it out in terms of this rho n, this Reynolds operator, and it's just a trace of this Reynolds operator. Okay, so that's the key point. And this trace of the Reynolds operator we can write in a different way. Okay, so how does this act on the P? Okay, well basically you let each of these group elements act on P. Okay, and these are all linear maps, the actions of G on this P. And then you take the average over this group. Okay, so since the trace is actually a linear function, okay, you can break up this trace of this rho n to a average over the group as follows, where the actions that you're looking at here, the linear endomorphisms, is the action of G on this P, and this P is inside Pn. So we're going to denote by the linear endomorphism the action of little g on that subspace Pn by this notation here. And we take the trace of this, and you take the average over the group, you get precisely the trace of this Reynolds operator. Okay, so it's actually quite easy to see why this is true. Hopefully this is something that you already know from your linear algebra. Remember, this is a projection. Okay, so rho n is a projection, so basically it's diagonalizable, and it has only a 1 eigenspace and a 0 eigenspace. Okay, so it projects onto the 1 eigenspace. Okay, and the algebraic multiplicity of that 1 eigenspace is of course the dimension of that space you're projecting onto. Okay, so what is the sum of the traces here? It's just going to be the dimension of this, which sums up all the 1s. So the sum of all the eigenvalues which equal 1, and the only other eigenvalue is 0. Okay, so that's of course the sum of the eigenvalues, and that's of course the trace of that matrix. Okay, trace of rho n. Okay, so that's very easy to see, and that allows us to use the Reynolds operator to look at this formula and prove it. Okay, so what I claim now is that we can actually break up this formula into bits according to each group element, and that will simplify our problem. And so the new thing that we need to prove is this theorem prime instead. Okay, so this is something we need to prove for each group element little g inside our group big G. Okay, so we just pick this term here, down here, 1 on the determinant of identity minus 5gt, and I claim we just need to show that it equals this power series over here. Okay, so the coefficient of t to the n is, instead of using this dimension, we'll replace it by the trace of this G acting on Pn, like that. Okay, so let's prove this new version of the theorem, and it's quite easy to see how that works. And it's just a simple calculation. Okay, so the first thing to realize is that, well, you're inside a finite group, so you have Lagrange's theorem floating around, okay? So that means the order of this element has to be finite. G to the m equals the identity in the group for some positive integer m. Okay, so that tells you, of course, when you apply the group homomorphism phi, that phi to the g to the m is also the identity. So that tells you that the minimal polynomial of this phi of g, what can you say? It divides x to the m minus 1. And that has distinct roots. So straight away we know that the important conclusion here is that phi of g is actually diagonalizable. Okay, it's diagonalizable. And once we know that it's diagonalizable, that makes it easy to calculate the trace, because then you can talk about the sum of the eigenvalues very easily, okay, in the diagonalizable case. Okay, so let's pick a basis of eigenvectors, x1 up to xr inside our V, okay, and suppose the eigenvalues are lambda 1 up to lambda r. Okay, so that tells you about V, which is P1, the degree 1 component. But actually now, since the group acts by algebra automorphisms, that tells you an eigenbasis for each of the Pn's and for the whole polynomial ring. Okay, so why is that? Because now you find out that every monomial is also an eigenvector. Okay, so if you have x1 to a1, x to the a2, times all the way down to x to the r to the ar, how does the group element G act on this thing here? Well, it acts on each of these, and you just multiply the action. So this x1 becomes lambda 1 x1, so that contributes, so that gets multiplied by lambda 1 to the a1. This x2 goes to lambda 2 x2, so when you raise it to the power of a2, that contributes lambda 2 to the a2, and so forth, down to, at the end of the day, we see that the action of G on this monomial is just to multiply it by lambda 1 to the a1 times lambda 2 to the a2 times all the way down to lambda r to the ar. Okay, so now we have an eigenbasis for the whole polynomial ring, and in particular for each of these Pn's. Okay, so that's going to make it really easy to calculate the trace. Okay, so let's look at the left-hand side here, okay, and see what that is. We can write that down straight away using the eigenvalues for phi of g. Okay, so we have 1 on the determinant. We'll pick the basis x1 down to xr that are listed here. Okay, and then with respect to that basis, what do we have? The identity is, of course, just the identity matrix. And since we have a basis of eigenvectors, you have a diagonal matrix here, and the diagonal entries are just the eigenvalues lambda 1 down to lambda r. Okay, you subtract here two diagonal matrices, so you're just taking a determinant of a diagonal matrix here. Okay, and one of the diagonal entries, they're going to give you the factors of this determinant. Okay, so in the denominator we have the first entry is 1 minus lambda 1t, so that's the first factor. The next one is 1 minus lambda 2t, and following the pattern we go all the way down to 1 minus lambda rt. Okay, so this is the bit that's written as a rational function, and this is as a power series. So let's see how that is related into a power series. And that's quite easy to do because there's the reciprocals of all these linear terms. Now you can expand as a sum of an infinite geometric progression. So 1 on lambda 1, 1 on 1 minus lambda 1t is just 1 plus lambda 1t plus lambda 1 squared t squared plus so forth. And you expand each of the reciprocals of these linear terms similarly. Okay? We want to show that it's equal to this product. Okay? So let's expand this. Okay? Expand this out. And the way we'll expand it out, we have to do it in terms of a power series, so we'll collect like terms and see what all the coefficients of all the t to the n are. Okay, so of course the constant term is 1 times 1 times 1 all the way r times is just 1. Okay, let's have a look at the degree, the coefficient of t now. Okay, so how can you get t from multiplying these r products, the r factors out? Well, what you must have done is you must have taken one of these r terms with a t in it, degree 1 terms, either lambda rt or lambda 1t or lambda 2t or one of the ones in between, and multiply that with one of the ones. Okay, so that's the terms that you get. So when you sum them up, of course, what is the coefficient of t? It's just lambda 1 plus lambda 2 plus all the way down to lambda r. Okay, so what do you notice about this? Okay, of course, these are just all the eigenvectors of, or the eigenvalues rather, of the vector space spanned by x1 to xr, the degree 1 part. Okay, so here this is just a trace of g acting on the degree 1 part, P1. Okay, so that gives you the right answer here. Okay, let's look at the coefficient of t squared now. Okay, so how do you get t squared? Okay, so I guess you can multiply 1t squared with lots of 1's, or a t with a t and the rest are 1's. Okay, so if you have a t squared term, okay, you'll have something like lambda 1 squared t squared, or lambda 2 squared t squared. So you'll get all the sums of the squares of each of the lambdas. So you get a lambda 1 squared, lambda 2 squared, all the way down to lambda r squared. Okay, or you can multiply a t term with a t term. For example, a lambda 1t with this lambda 2t. Okay, so you also get the products of different lambda i's. Okay, so you get lambda 1 times lambda 2, lambda 1 times lambda 3, all the way down to lambda 1 times lambda r, and also any product of two which are different. So at the end of the day, what do you get? You get the products of all one of the lambda 1's down to lambda r with another such lambda 1 up to lambda r. Okay, so what are those? Okay, well, they look basically things of this form. Okay, they're things of this form, except for where the sum of the a1, a2 up to ar is equal to 2. Okay, so it's either two different ones, and lambda I times lambda j, I and j different, or it's a lambda I squared. Okay, so what you're doing there is you're just summing up all the eigenvalues for things where the monomial has degree 2. Okay, and the monomials which have degree 2, that's an eigenbasis for the P2, the degree 2 piece of the polynomial ring. So of course we see again here, okay, here this is just the sum of these eigenvalues for G acting on the degree 2 piece. So of course it's just a trace of this G acting on the degree 2 piece. So that matches up here as well. And if you continue on looking at the high coefficients, hopefully you can already see the pattern. You'll see that in fact what this expansion equals is precisely this right hand side here. Okay, and to see that you just need to use this fact here. Okay, just use the eigenbasis for Pn and realize that it equals the following eigenvalue. And thus we arrive at Molien's beautiful formula for the Hilbert series of polynomial invariant rings. I hope you enjoyed this adventure in pure mathematics.